Good morning, everybody. We are going to talk through the practice exams today. And then, so we're starting with the fall one. We're not going to do too much on these. Let's see, where's my little. Here we go. Don't worry about. My muted still? No, okay. Is good. There we go. Okay, now it's working. Don't worry about these. Name the functional group ones. We're not going to do that. Look at this aromatic ring here. This would be, we have a chlorine in our meta position. We've got an aldehyde. This is metachlorobenzaldehyde. I don't know if we've ever talked about if you have an OH and it's not, or both an OH and aldehyde, you can treat an OH like it's just a regular substituent. If you do that, you refer to it as a hydroxyl group. So for this here, if we're numbering, so we go through aldehyde first because that's gonna be our highest priority group. We have 1, 2, 3, 4 here. So 4 carbons is a butanal. We have a chlorine on 2, a hydroxyl on 3. Doing some RNS. I'm gonna redraw it. Chlorine to be our highest priority. And then we have carbon double bonded oxygen on one side, carbon single bonded oxygen on the other. So this should be higher because you have the double bond. So that would be R. OH should be 1, Cl is going to be 2, methyl is going to be 3, counterclockwise should be S here. So putting this all together, we're going to have a 2R, 3S. Chloro is going to be first, 2 chloro, 3 hydroxyl, butanal. So the chlorine is second because you have a direct bond to this oxygen versus you have a bond to a carbon and then the chlorine. All right, I'm going to switch over.
The first one. How do you know it for the first naming? how come the aldehyde isn't in the second position? Why is the chloro in the meta position? I mean,
Why is it in the meta position?
yeah, why the chloros in meta position, not the aldehyde?
Oh, it's mostly because we don't have an easy way to name a aldehyde group. So sometimes you get like if it was a nitro group, there'd be two answers. This here could be either metachloro nitrobenzene, or meta nitro chlorobenzene. We don't have like a shorthand name for aldehyde, so you're gonna have to put it as metachloro benzaldehyde. Does that make sense?
Yes, thank you. So from the first group, we did in the lecture from, I think it was Friday, we will use that and then decide what is it, the meta or para. Is that correct?
Yep.
Okay, thank you.
All right. We are not going to do NMR. You can cross it out. And cross this one out. We never covered this one. So taking a look at the first reaction here, we have an OH, which is a group 1. We have a methyl here, which is a group 3. So our group 1 is going to trump. It's an orthopara director. We can either add to this position or this position. Chlorine is pretty small. Our other ortho is blocked. Chlorine is pretty small, so you're going to end up probably getting both in pretty good yield. So this could lead to either of these two products. All right, going down the line, we've got it's a combination diol and thiol, but it's going to follow the same principles. So you'd protonate, you'd make N-acetal using both sides of this compound. We can get something that looks, doesn't matter which side you put oxygen or S on. We've got 3 carbons between them. And because there's no stereochemistry, these are the same compound. You could draw it either way. All right, taking a look at this aromatic ring. We've got a tert-butyl, which is going to be a group 3. Orthopara director. It is quite large. It's going to be blocking your ortho position and you're going to really favor that para. we've got two equivalents of it. So if we do this reaction once, we should get this here. We can now have this interact with another equivalent of our starting material because we said we had two equivalents of it. It's still an ortho-para director. It's still going to favor the para position because it's so large. This should end up forming something like this here. Okay, for our next one, we've got.
So that's it. The last one will be the last answer, right? The final answer is the last one, right?
Yes.
Thank you.
Yeah, this is just like a halfway point. All right, so we've got I think I actually gave a wrong answer on the key. We've got MCPA and a ketone. Our hierarchy is going to be H followed by tertiary. Secondary, phenyl, and then primary here. So we have phenyl on this side, and we have secondary here. So it should favor the secondary side. We're to do an oxygen insertion. And it should give us this ester. I think this is one where the key is marked wrong. It shows it on the other side, but it should insert into this end. All right, we've got a primary amine here with a proton. So it's to make an amine. Our nitrogen is essentially just going to replace our oxygen. Nitrogen had a methyl group on it, which it'll retain. Going back up to the top, this is going to be our elimination addition reaction. So we can make two different alkynes out of this. Each of them can lead to two products. Taking a look at the four products we made, two of them are the same. because we made something twice, it's going to double the amount of it that was formed, which is going to make that the major product.
Can you please do an example of the BR was on a para position instead of meta?
Yep, I'll do one after this page. I'll like draw it up on a.
Okay, thank you so much.
Yep. Okay. We've got a secondary amine, which means we would originally form this positively charged imine here. From this point, we can have our starting material come in. There's probably two answers you can get here. This side might be a little bit blocked by the methyl group that's next to it, relative to the side I'm drawing in red. But really, you could draw either answer to this one and it'd be fine. So this would be one possible answer. Other one would be where that double bond forms the other side. Because they're both secondary centers, both of them are possible. Okay. All right, we're doing a Wittig, which is essentially just a reverse O's analysis. So we're going to be losing our oxygen and our triphenylphosphine. They're going to be combining together. Oh, that's too many carbons. For this one here, stereochemistry isn't going to matter because it's symmetrical for one of your molecules. All right, last one, we've got benzaldehyde. This is a group 5. That's a meta director. So our aldehyde here, or our ketone here, is going to end up adding meta. All right, let's do one of these top examples. I'll do one where it's ortho and one where it's para, just to go through some other ones. Give you guys a second to finish writing. Okay, so if it is para here, there are the two different alkynes you get are going to be the same. So realistically, we could get, or hypothetically, we could get either this alkyne from an elimination or this alkyne. But because they're the same molecule, it doesn't really matter which one you draw. All right, and that's because you're pulling off protons. So you have a proton here and one here. They're both going to give you similar alkynes. Our amine can attack. So I'm just going to draw it attacking on one. It can either attack here or here. They are both going to lead to a product. And because in our first step we had the same amount, it's going to lead to 50-50 ratio of both of them. Alternatively, if it's ortho, the biggest difference is that now we only have one hydrogen we could pull off. The other side is a methyl group, so we can only really make one alkyne in this case. And then from here, both of these alkynes can form a product. So this would also get two products. Neither of them being a major one. The only time you really get a major one is when you have it meta. So now we have two different hydrogens. They are both unique. They can make two unique different alkynes. Both of these can form their own unique products. So it'll randomly happen. 50% of the time we'll get this alkyne. 50% of the time we'll get this alkyne here. They can both lead to a product or two products. If the top parts both happen 50% of the time, that means it's going to divide it down to 25% for these. Because these two are identical molecules here, we have two portions of 25%, or 50% of our molecule being this. And that's going to make it our major product because there is the largest number of it. We have 25, 25, 50. That makes this one major. Giving us this for a major product. All right, let's go on to the kind of maybe mini synthesis is a good way to describe them. Okay, so for this we need an alcohol. There's gonna be two different ways you can do this. The first way is depending on what type of ester you add. So I'm gonna do both of them. You could either add the methyl ester, so oh my gosh. If we do this acylation, now in order to get our product, we're gonna need to add this isopropyl group here, most likely as a Grignard. This will get us to our final product. The other option is that we could add the other ester. Oops, not what I want. So if you instead added this ester, now all we need is a methyl Grignard and water. Both of them work. You're both doing kind of the same reaction. Just depends on which part of your group you want to add first, which one second. So you can either add the red highlighted group first and the blue, or the blue and then the red. Won't make much of a difference. So Grignard reactions are always going to reduce. They add a carbon group, but they also reduce down to an alcohol. So it's going to happen naturally through that reaction. Like if you think of your normal Grignard, and then it picks up an H to get to your alcohol. Grignard is just naturally a reducing reaction. This next one's probably longer than something I'm going to give you guys. But let's just go through it. So a couple of different ways you could do this. I would probably add in a small base first. It's going to let me do an elimination. And then BH3THF. And peroxide. Nope, just alcohol. Gets us mostly set up for what we, I guess I could have drawn this in the box. Set up for what we want. From here, we need to oxidize. You could either use chromic acid or PCC. These are a little easier to write, so I'm just going to put this one here. That gets us to our aldehyde. And then finally, H plus and this amine will get us to an amine. Enamine for this one. It's because it could be a secondary amine we're adding in. And I'll go through a mechanism for that on one of the next couple pages. All right, so we need some sort of ketone to do the next one. We would want to add PCC instead of chromic acid. Chromic acid is going to take us all the way to a carboxylic acid. So adding in PCC as our softer oxidizing reagent. Come on. And then, looks like I'm starting here. From this point, we're trying to form a cyclic acetal, so we need to add in a diol. H plus, we've got 2 carbons in between our diol. Should add this here. For our last one, we have an amine and a Cl. They are meta to each other. So in order to get them meta, we need to have a meta director on there at some point. In order to make an amine, we want to go through a nitro group, which is the meta director. So probably best to add that first. If we add the chlorine first, we have an orthopara director, and that's going to be problematic. So first starting off by throwing in HNO3, H2SO4. This is a group 6. It is a meta director. So from here, if we want to chlorinate, Cl2, AlCl3. And then finally, to reduce this down, we need to throw in iron HCl to get to our product. All right, so most likely this one is harder than anything you guys are going to see in your exam, but the rest of them are probably pretty fair game for the number of steps you might see. Let's take a look at the next page. Nope, not what I want. And then probably take a little break. So you can cross out this one. We didn't really go over these. The top one is much harder than it looks. The reason for that is if you chlorinate, you've got an orthopara director, which means you can only really make this or this here. So in order to have it add meta, we're going to have to go through a diazonium pathway in order to add our chlorines. That way, we can have them end up in the correct positions. So I'm going to erase what I drew, walk through a way to do this. I think there are maybe 1 or 2 different ways to do it. You can also use a directing group for it. But we didn't really go through how to use those, so we're just going to go through this one. I think it's a little more straightforward. So if I add in HNO3, H2SO4, I can add a nitro group. It is a group 6. it's a meta director. From here, if I want to throw in Cl2, AlCl3, I can get these two meta to each other. Now I have to turn this NO2 into a Cl2 or Cl. So if I reduce it, go through my diazonium pathway, so iron, HCl, NaNO2, HCl gets me to a diazonium. And if you remember from that large chart we made, probably on Monday, if you add in copper chloride, this can take a diazonium and turn it into a chloride. We'll do the mechanism ones and then take a break because we got a little bit of time, about 7 minutes until it's 10 o'clock. So well, let's take a look at those. So last page from the fall exam. We've got an enamine synthesis for the first one. Our first step is always going to be the same. We are going to pick up a proton. From here, our amine can attack. If you guys just want to draw a quick transfer, having the oxygen pick up the proton, I'm fine with that. So oxygen can pick up this proton here. We can make water. Our amine can come kick out that water. To make our amine. From here, we have a pretty large nitrogen base in solution. We've got some different protons. We've got a tertiary one and a primary one. Diisopropylamine would be considered a large base. So this would pull off a proton from this less substituted position in order to give us an enamine product where the double bond is on the primary position. All right, for this next one, we didn't really talk about how to do this, but it's a very simple concept, so I'm just going to walk through it. Essentially, we have a group 1 here. This would be a group 2. And this would be a group 5. Whichever ring has the highest group on it is the one that's going to be activated and then derivatized. So we can essentially just ignore this whole ring here because it's only got the group 5 on it. We're just going to use this group 1 as an orthopara-director. All right, we're adding a nitro group, which is pretty big. It's most likely just going to add the para position. I'll just move this whole thing up. I can. Nope, not really. Okay. I'm going to erase a lot of this so I have some more space. There we go. Okay. So group 1 here. This is the group we care about. It's an orthopara-director. This is really big, so we're most likely just going to add to the para position. It says please show resonance prior to the attack of the electrophile. So our resonance structures would look. Oh, those things are huge. All right. Like this. And the last one should be here. All right, so we need to make our electrophile. We've got HNO3, H2SO4. Sulfuric acid is the stronger acid. So if this oxygen comes in, we can grab a proton here as well as kicking out water. This will let us generate this nitrogen electrophile. Our aromatic ring can come in and attack it. We're going to lose our aromaticity. Wrong spot. Our HSO4 minus can grab it. This proton, re-aromatizing to give us our final product. Which should look like this here. I'm going to circle it because it's getting a little messy. Should look like this here. Okay. Let's take about a 8-minute break. So meet back here at 10:10. We'll go through the spring exam, which I think is a little bit simpler. So I'll see you guys then. All right, let's start looking at the spring exam. So instead of NMR, this is what we're going to do. We'll do some nomenclature on one page. We'll do some of these aromatic, anti-aromatic, non-aromatics on the other page. Let's get started with this. First one, we've got an oxygen and a nitrogen. For the oxygen, only one of its sets of lone pairs is going to be considered delocalized. The other two are going to be classified as localized. So for this here, we would count the two blue lone pairs. So two sets of lone pairs. We have two double bonds. That's going to give us a total of 8 pi electrons. Our normal rule for aromatic is going to be 4n plus 2. So that would be, if our pi electrons are equal to 2, 6, 10, 14, 18, etc. Anti-aromatic is 4n, so if our pi electrons are equal to 4, 8, 12, 16, etc. This compound here has 8 electrons, so this should be anti-aromatic. We've got double bonds on all these nitrogens, which means that they are, I'll draw my other color, going to all be localized. There is already something in that pi plane. They cannot exist in the same one. So because of that, we are only going to count the double bonds. This has 4 double bonds. So 8 pi electrons again, and again anti-aromatic. Let's see. Most of these have a double bond on them, but this nitrogen here does not. So we have one set of delocalized, 4 sets of localized, 2 double bonds, 1 delocalized lone pair. That's 6 pi electrons, which is in our aromatic category. sp3 center, non-aromatic. Okay, we got 1, 2, 3, 4, 5, 6, 7 double bonds, which is going to be 14 pi electrons, and aromatic. Should be a pretty straightforward page. So this will be replacing our NMR, which means we can cross out this page. Yeah, that was an easy one. Let's see. I want to say we talked through everything on this page here at some point. So our first one is our Birch reduction. We've got sodium. We're going to be adding electrons into our ring. Because we have an electron withdrawing group here, it's going to want to generate a negative charge. At this position, so it's going to have the most resonance it can. Tornado alarm going off in the back road. So we're going to end up with a double bond pattern that looks like this from our Birch reduction. We've got a Wittig next. We'll generate triphenylphosphine oxide as well as essentially clipping and sticking these two together. Someone asked if there's going to be any reactions where no reaction occurs. No, I'm not going to do anything with that. So don't worry about these. All should have an answer. There's never going to be no reaction as your answer for these. All right, we've got a hydrazine here. So we're really just going to treat the other nitrogen like it's along for the ride. Doesn't matter which one you pick. They are both just nitrogen. So we'll form a normal imine as if this was a primary amine, which it kind of is. And our second nitrogen is just thrown on there, or tacked on as well. All right. We didn't really do zinc HCl. We only really did iron, but they both do the same thing. It's going to allow us to reduce this down to just an amine here. Our KCN is going to act as a nucleophile. HCN can protonate. Either of those steps can kind of happen in any order. I'll draw it attacking first. And then you'd protonate, get an OH, C triple bond N. Pretty straightforward, essentially the same thing as a Grignard. All right, doing some aromatic substitution reactions. We've got a group 4 and a group 3 here. Group 3 is the orthopara. We're going to favor that one. Our para is blocked. So these two orthos are open. Symmetrical doesn't matter which one it adds to. You have fuming H2SO4, so we're going to be adding a sulfate. We're up there. And you can add either the top or the bottom, doesn't matter because it's symmetrical. All right, we have a secondary amine as well as a secondary and tertiary center. Because an amine acts as a large base. We are going to be treating it like a large base. And we're going to be forming our double bond in the less substituted position. So we'd originally form this imine here, and then we're going to deprotonate our left substituted position in order to generate our enamine. Action's a little rough. Like so. All right, we got an elimination addition reaction. We went over these pretty extensively on exam, early fall exam, so we'd end up making an alkyne. Here, either of them, they're both symmetrical. So we can end up with two different products. We can either form our amine at this position or at R. So either para or meta to this toluene. Forming a thioacetal. We've got 3 carbons in between our thiols, so it should make a 6 when we're doing. So sulfur, sulfur, 1, 2, 3. We've got a group 6 and a group 5. So group 5 is our higher priority. It's a meta director. So it is going to add to this position, and we're going to brominate. Giving us this product.
Excuse me, so the last question. So if we have the excess BR, so we have got 2 groups on the meta position, right?
If you had excess BR, that's gonna give you a mess. So you would first add it to here into the meta. Now your meta group is a group 4, which is an ortho para director. I wouldn't worry about this. I think you're thinking of like if you have NVS in excess. Then you can add multiple BRs. There's no hydrogen here left, so you can only add a BR to that position. If you did this BR2 reaction in excess, it would be a huge mess.
So that means if the last question, if we have the PR excess, react with that formula, so phenene, and then we just got only one meta position, right?
Yeah, if you did that in excess, and we never really talked about this. So you'd originally, your first bromine is going to go meta. Now you've got a group 6, a group 5, and a group 4. So your group 4 is your higher priority. It's an ortho para director. So now you're going to add a bromine here, here, or here. Because you're in excess, you can add it to all those positions. But again, we never talked about this, so I wouldn't expect to see this on your exam.
Thank you.
You're welcome. All right, this first one is something we didn't talk about. This is protected group theory. You can cross this one out. Okay, we need to add two groups. They need to be meta to each other. This is a meta director. This is an orthopara. We're going to add the meta director first. Now that the meta director is added, we can add this methyl. And get the right stereochemistry. All right, to get fluorine and bromine, meta to each other, we're going to have to go through our diazonium pathway to get the fluorine in general. So adding HNO3, H2SO4. Gets us a meta director. We could add in our bromine now. From here, we're just generating our normal fluorination. So FeHCl gets us to our amine. NaNO2, HCl gets us to our diazonium. And then HBF4 can get us to a fluorine here.
And in synthesis problem, this is what we expect to do too, right?
Say it again.
In synthesis problems, this is similar of what we need to do.
Yes.
Okay.
Last one, we need to make an imine. So we need to oxidize either with PCC or chromic acid. And then we can just throw an H plus and our ethylamine here. The third one's a little long, but the way you make fluorine is always the same, so that one's probably not as ridiculous of a question. Let's take a look at the synthesis questions. I think you can only do one of them again. Oh no, we can do either of them. Okay. Oh no, we didn't really talk about this last one. This uses something we never talked about. I think we almost did this top one in class. May have done it. There are a few different ways you can make an alcohol. I'm going to go through the MCPBA one. So if I add in this acyl chloride, AlCl3. I can make this ester or this ether ketone here, throwing an MCPBA. Well, then let me make my ester, which I could reduce LH. From here, we've got an ortho para director. Adding our ester in group is probably going to be the easiest thing to do next, or adding our other ketone. So taking the same reagent. Next steps are a little unspecific, so we could either add in the nitro now or do the MCPBA. It doesn't really matter. I'm going to throw in HNO3, H2SO4, add the nitro group. And then MCPBA will give me my final product. A couple of these you can move around, still get the same answer. You could do the MCPBA before the HNO3. I think you pretty much have to make the OH first in order to get the proper configuration. Although not necessarily. I guess you could add in the, no, you're running into an issue there. So if you add in the top ester first, you're not going to be able to selectively reduce down to an alcohol. You're going to get 2 alcohols or 2 esters. So this is probably the only way for the start of this that's going to work out. So what I mean by getting 2 esters, if we try to do the top part of this first, and then if we try to add in the bottom portion of it, we throw an LAH at this point. There's no reason to pick one over the other. This is going to lead to a diol. And you're going to be stuck, which is why you have to make the full alcohol first before you can do one or the other. This is the dead end you can run into. So you're most likely to have to make the full alcohol first before you do any of the other parts of this. All right, let's talk through the mechanism from the spring. What happened? All right, so we are doing amine formation. We can pick up a proton. From here, nitrogen can come in and do an attack. Our oxygen is basically just going to be along for the ride. we can have a proton hop from the oxygen or nitrogen to the oxygen. So grabbing one of these. Kick out this oxygen. Give us a protonated final product. Then either have water or another amine pull off this last proton to give us what will be referred to as an oxime here, but really just an imine with an OH on it. That was the same reaction. All right, well, we have a group 3 and a group 4 here. So our methyl here is a group 3, Br is a group 4. We're to care more about that group 3. It's an ortho para director. Our para is currently being blocked, which means it could only add ortho. We have HNO3. We also had last time. This can form a double bond, grab a proton, kick out that water in order to make our electrophile. Our aromatic ring can then attack it from the ortho position. And then we can pull off that last proton. In order to generate our final product. All right, so that is the spring 2021 exam. Are there any questions from you guys?
So we will have 6 questions or 5 questions on the same.
Should be 6 questions. So you'd have a nomenclature, a aromatic, anti-aromatic, non-aromatic. Fill in the, what is this, 5? Fill in the fill in the major product. A like little box synthesis ones where you're doing the reagents, your regular synthesis, and then a mechanism page.
So we have the recitation tomorrow too? Oh no.
Nope. So we're not going to do recitations on Thursday or Friday, either this week or next week. So we'll have a recitation today. We'll have one Monday and we'll have one Wednesday. All right. That is all I have for you guys. If there's no other questions, I'll see you guys in recitation today.